Hey, how's it going? So yesterday, in the middle of my stream, I spilled coffee on my computer. So I had to stop in the middle of it. Today, what we're going to be doing is continuing getting different optimization methods. So, um, I've copy and pasted a list of optimization methods here from Wikipedia, and I'm going through trying to implement them. Um, so yesterday I implemented Bayesian inference. Let me make sure. Oh, oops, don't want to share my email. Let me make sure this is working. Okay, so this we could break out, put down here. Don't want to miss any chats. And then if we look at our Trello board, um, make sure I did the right date, 16. Yep. Okay, so right now what we're doing is adding different optimization techniques. We also want to optimize each using Bayesian. So if we go here, optimization data, training years test, we've optimized triangle with the Bayesian technique. So while this runs, or we can let, we can set up a optimization and let it run um, while we're changing the code. So let's go down here to our tests. Test training years we want to be on. Now we're showing the plot. It's showing a plot every time. So perform optimization, years to train on. So does perform optimizations bring up a plot? Oh, training years test. Test training years equals true. Training years test. For year and num years, make the directory. If it doesn't exist, then perform optimizations. All right, perform optimizations. Region params. If show plot is equal to true, fig.show. Are we doing plot.show anywhere? Get training years plot. So here we could say show plot is a bool that defaults to false. And then this should be if show plot is equal to true, show it. Training years test. So at the end of training years test, we get training years plot. Then show is equal to true. Okay, so now we want to optimize. We want to do each technique. So we've done triangle, so we want to do rectangle and hybrid now. Modified triangle might give good results as well. So hybrid method. Get training years. Okay, training years test. Free circle 2. Okay, so this one I didn't save. So this one we're gonna call modified circle. Oh, not modified circle. modified triangle, and then set up a, what is that? Okay, cancel. I don't know what the hell that was. Alright, so modified triangle, and then we want to run. I'm having trouble getting my damn M key to work since I dropped coffee on my computer. And then do Bayesian optimization. Now let's go up here and say, let's make sure that we're optimizing for percent return because I was messing around with that this morning. Optimize line location. Okay, we're returning negative percent return, and we just want to go to assess region, percent return, equals profit divided by risk if risk is not equal to 0. Otherwise, it's 0. Now we need to find another objective to optimize for. Find new objective to optimize for. Okay. And the reason we want to do that is that the percent, just using percent returns, sometimes optimizes to only choose one bet. If you are choosing 1 or 0 bets, then percent return strategy sometimes optimizes. If you're choosing 1 or 0 bets and the one bet is a win, percent return is constant at 0 or 100%. So we're either returning 0. Oh, that's not true. We're not returning. So it's either 0 or positive. If taking any. Okay, my dog's barking. Gotta get her to stop. Okay. Here's Riku. All right. So, if taking any negative, or if taking any losing bets, so if we're taking any losing bets, percent return could, now the other dog's barking. Come on, Riku. Don't follow her lead. Okay. So we want a new objective to optimize for that's gonna take away the problems that we're having, in particular with the circle method. Okay, so, all right, we're returning the right value. Now let's go. Uh-oh. Love you. Good luck. Have a good lesson. Thanks. Okay, so we're gonna wanna optimize here for the modified triangle. So we can run the script now. Analysis 1.py. Bounds is referenced before assignment. So we don't have any bounds. I thought I wrote bounds for modified triangle, but I may not have. So bounds, do I call it a modified triangle? Region, get region. Yes, a modified triangle is a region. We just haven't added any bounds for it. So elif region type is equal to modified triangle. Bounds are equal to, and I think modified triangle also only takes in one parameter. What did it say about hybrid? Same as hybrid with b fixed to minus 180. So yeah. Okay, that should work. Modified triangle bounds are equal to, it could go from minus 1000 to 1000. So if region type is modified triangle, it could go from minus 1000 to 1000. And add the comma there to make it work. And run it. Now let's see what it does. And then I also want to do an optimization for circle. But I want to make the bounds smaller. So here are bounds. So we were saying it could go between minus 1000 to positive 1000. Which is pretty huge swing in location for the center of the circle. I don't think having the center of the circle here would do anything for us. I think we could make the center of the circle have to be between like 0 and 500 on the X, and on the Y minus 500 to 500. Okay, so if we're dealing with a free circle, we can go from minus 500, no, we can go from 0 to 500 in X, and then we could go from minus 500 to 500 on Y, and then the radius, where's that plot we were looking at? So now I want to see how big could the radius be. Maybe like 200 or so. 200 should probably be less than 10. I mean, with a radius of 200, that's a big circle. So we should say, let's make the radius go from 10 to 200. 10 to 200. Now the parameter space is a lot smaller, but we're kind of still looking for that same region. So let's go down here, take off test training years, and then we could turn on perform optimization analysis. Perform optimization, test years, num years to train on, region type is free circle, optimization type is Bayesian. So we already have everything we want there. So let's go to a new terminal and run that file. Okay, Now that will run. Is there anything else we want to look at? We want to do training years test for all bound types. So we haven't done it for rectangle. Let's do it for hybrid. Oh, okay, I did it for hybrid. I did it for triangle, both types of optimizations. I haven't done it for rectangle. And I'm doing it currently for modified triangle. Free circle, I don't want to do it until we could get better results. Did I put it in here? Well, free circle doesn't give us much. But I guess I didn't put it in here. But free circle will optimize just for like a single point. So yeah, free circle isn't working right now, but we can add the optimization for, damn, I keep forgetting. Oh, rectangle. So here we can say the directory should be rectangle. And the technique should be rectangle. Okay. Now, let's go up here. All right, what do we want to do? I guess we just want to run it. We just want to take off, want to make our booleans do what we want. So take off perform optimization analysis and turn on test training years. And we're going to run this file one more time with our current updates. Make sure it's saved. Python 3 analysis1.py. Okay. And then once we've finished this more basic analysis, we're going to try machine learning grouping for group in for wins and losses. And that is medium priority. And we can move it over into the to-do because we're probably not going to get to that today. Okay, so add different optimization techniques. So we have all our stuff running here. Let's just put that there so we know when it's done, because this will be the first one to finish. And let's go look at that actually. 16th. Huh. So we're still this plot doesn't look good. 2016. Okay, so it's doing a free circle. Now what did it find? Didn't even put the circle anywhere. And it found that, okay, so we messed something up with free circle, because it's not even drawing our circle. man. All right, so if we go back to optimize line location, let's make sure our other plots are working. So we set up in training years test, we set up the rectangle test and modified triangle. Region type rectangle. A, B, profit, percent return. Yeah, so it's returning profit and percent return. We'll have to wait to see what it optimizes to see if it draws the region. We can go look at modified triangle though. 7:47 a.m. What's up with the time? Huh. Well, it didn't do a lot of optimizations. That's just for 2008. What about for 2011? Oops. 2010, what did it find? Okay. That's good. Okay, well, we're going to keep that up so we can watch it. The first column is the percent return. The second column is the total profit if we're betting $10 bets. All right. So those are working. Back to the circle. The circle isn't working. So free circle, the X is going from 0 to 500, Y is going from minus 500 to 500, and the radius can be between 10 and 200. So what radius does it say that it optimized for? All right, 2016, results, HKR. So it said the center of the circle is at 319 minus 500, and the radius was 151. 319 minus 500. Huh. Okay, that circle is not showing up there. It also showed that profit didn't change. But here we see that it does change. So what's going on with the circle? Let's exit out of here. Make sure that the parameters are right. HKR. Yep. But why is there no change in profit? Yeah, why is there no change in profit? Okay. Um, so that is an unknown. This though is still going strong. Um, good for 2011, but um, but the year we struggle with is 2018, so we don't really care that it was good in 2011. Actually, the training year's test, all we want is something to we want something to return positive for 2018. So perform optimization analysis. I can say years to test is equal to 2018, region type free circle, free triangle modified triangle, and we're going to do an Bayesian optimization. And then, so for that, we want perform optimization analysis to be on. Change this to 1 and run the analysis. So now it's not doing anything for the free circle, it's doing modified triangle instead. Okay, so that's running. Now let's go back and look at the types of optimizations we want to implement. All right, so now we have evolution strategies. Evolution strategies take a long time, put off for now. Same thing with genetic algorithms. We can come back to those later if we're still having trouble optimizing. Okay, MCS algorithm, I don't know what that is. Multi-level coordinate search, combines global and local search. All right, MCS algorithm, Python. SAT solvers. Those are complicated. No easy Python implementation. Now Nelder-Mead is easy. That's in SciPy. I've used it before. I just have to remember how to use it. From SciPy to optimize, import, minimize dot Nelder-Mead, I think. Something like that. From SciPy to optimize, import, minimize dot Nelder-Mead. Okay, from SciPy dot optimize. Okay, differential evolution. And we also want to import minimize. And then we can say Nelder-Mead. Does Nelder-Mead use bounds? Yes. So then we could say otherwise if optimization type is Bayesian. Otherwise if optimization type is equal to Nelder-Mead, then we're gonna say res is equal to, just going to do that there for consistency, although we never call res. Res is equal to minimize function x naught. Do we need to specify x naught? Um, why does it take us here? Minimization of scalar function x naught, initial guess, array of elements, size n, where n is the number of independent variables. What if we don't specify an initial guess? Here we go. X naught. All right, so we've defined our bounds. Let's go see if we could get x naught as just the minimum bounds. All right, so bounds is equal to minus 1000 to 1000 minus 500 to 500. All right, now I for I in bounds. Oh, this is easy. We could just do I of 0 for I in bounds. Or even better, we could get a random value in the bounds. NumP random. Or we could just always start. Let's see. So accent we could start at 0. Rectangle we could start at 0, 0. Yeah, actually it'd be better just to get the let's get the midpoint of the bounds. I of 0 plus I of 1. Take that whole thing, multiply by 0.5. Cool. And that gives us the midpoint. So back up to where Nelder-Mead is. So if we're doing Nelder-Mead, then x naught is equal to 0.5 times I of 0 plus I of 1 for I in bounds. So now our start point is the middle. So initial guess is midpoint of bounds. And then res equals minimize, and we want to minimize optimizable func x naught, and we want to say bounds are equal to bounds. Okay. Now I think that should work fine. Now we have to go test it. Whoa. Did that already finish? I guess it did. So group optimization 16.1 results. So it returned positive for 2018. That's excellent. Because most don't return positive for 2018. Nice, so that's the region it got. Now, back to analysis 1. Is that going to return positive for every year? Where are Booleans? There we go. Nice. So perform optimization analysis is 1. Now, if perform optimization analysis is true, let's do this on all years going back 9 years. So going back 9 years, we have 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12, 13, 14, 15. Nice, that gives us 9 years. Okay. Now, let's exit out of here. And then we're going to do analysis 1. I think this should work. Okay, cool. Now we're going to want to take this off. We want to test the Nelder-Mead. So test optimization is equal to 1 if test optimization is equal to true. Region type, let's just make it triangle. Optimization type is Bayesian. Okay. Oh no, not Bayesian. Optimization type should be Nelder-Mead. Now let's go up here. There's the optimization type test. So we're going to want to add to that. Actually, we just want to add to valid optimization types. And we're going to include Nelder-Mead. Save it. Now we have yet another terminal window. Hopefully computer isn't maxed out, but it is. It's at 100% CPU. All right. So let's go back to our directory, spread, history data. Then let's go and run. Is this ready to be run? We have Nelder-Mead. Test optimization is on. Everything else is off. Triangle, Nelder-Mead. Okay. So this should test the Nelder-Mead optimization. So if it works, it'll start running. If it doesn't work, we'll get an error right here. Nice. Whoa. You already finished? I know that Nelder-Mead is fast. In the past, when I've done Nelder-Mead, it, sorry, I'm thinking. In the past, when I've done Nelder-Mead, it optimizes really fast, but doesn't get us to a good solution. So that's why I didn't start with it. I started with differential evolution because that's, so Nelder-Mead ran one iteration and decided it was a good result. Got to figure out more about the Nelder-Mead method for that to be useful, but it works. All right. Successfully implemented, but I'm not sure if this will be useful for us. Okay, particle swarm optimization. Lots of these seem like they're really computationally expensive. Okay, what's a particle swarm optimization look like? Okay, can we implement it in Python? PySwarms, nice. Okay, so here it looks like they're just plotting the data. Plotted the function, then created 20 particles at random locations. Okay, from this we can already find the G-best as the best position ever found by all the particles, since the particles did not explore at all. Their current position is their best. Yep, okay. Compute and plot the function, find the global minimum, hyperparameter the algorithm, create particles, initialize data. Okay, so this guy implements it by hand. Alright, tutorial for by hand implementation. Available here. Alright, so now we have pattern search, Powell's methods. I know that Powell is in SciPy too. Now let's go look at our optimization, see how that's going. The one we set up that we want it to do on several years going back using the modified triangle and the Bayesian method. Damn it. So already it loses money on the first year. Okay, so let's forget about this. Did well in 2018, but it performs poorly for the first year. So let's turn test training years back on. And then we're going to do the training years test for the modified triangle. I'm just going to look to make sure I don't already have that written as a directory. Bayesian triangle, free circle, modified triangle. Did I set that up earlier today? Yeah, I guess so. All right, modified triangle on 1 year of training data. Okay. All right, so back to implementing the optimizations. We only have a few more. So pattern search. Let's go figure out what that is. Pattern search optimization. Okay, so pattern search is a broad category of optimizations. Okay. Golden section search. So Nelder-Mead is an implementation of pattern search. Random search. So is random search implemented in Python? Okay, Python. Oh, I forgot. They want you to pay for stuff now. How does random search? So it looks like we have to implement that by hand in Python too. family. So pattern search is a family of algorithms of which Nelder Mead is part. Okay, now scipy.optimize.minimize method equals Powell Newton CG continuous Galerkin. I don't know if that's black box. Okay, so let's use the Powell method. This should be pretty easy. Valid optimization type, optimize line location. Okay, so we're gonna add Powell to the valid optimization types. And then down here, we're gonna say elif optimization type is equal to Powell. We're gonna do the same thing as Nelder Mead, except, oh, okay, so this wasn't even doing the Nelder Mead algorithm. We have to say method is equal to Nelder Mead. All right, comma method is equal to Nelder dash Mead. Okay. Now, how do we do the Powell algorithm? Okay, that's easy enough. So this is the same thing, except method is equal to Powell. Okay. So Powell method works. Now let's turn this off and turn on test optimization. And then perform the optimization test. Test optimization, I think, is still calling Nelder Mead. Yep. Okay. So it optimized really fast again. That's not much of a surprise. So optimization data, single optimizations today, one. Okay, so now it ran twice and optimized. Okay, so that at least works. Now let's go make sure the Powell method works. Okay, nice. Now back up here, added implementation, easy because it was in scipy.optimize.minimize. Random search, we already looked at that. Needs custom implementation in Python. Simulated annealing. Okay, the Powell method finished. Let's go look at that. Okay, again, didn't see a big change in profit. So that's kind of, oh, I think I might know what it is. What is wrong with that profit plot? We just need to find our optimization function, which is here. So we're plotting, results axis. Okay, we want to add data of valid region types of region type of C. Data of valid region types of region type. So data of data equals pd.read_csv of file name. So it's going to read that. Now data of valid region types, so data of region type, valid region types of region type, oh, of C, so that gets the parameter. Okay. But add subplot, num rows, num column. Okay, so we're scattering that against data.profit. Now, profit. Then we add profit and we add percent return. Why are we adding a comma at the end of percent return? It's weird. So get rid of that comma. No reason to have that. Now we can, when we're writing the labels for it, profit, comma, it should just be actually before profit, percent return, and then profit. I think that's right. Percent return, profit, yep. Okay, now let's try running that again and seeing if the parameter plots look like they're fixed. Taking longer this time. Might be taking longer to optimize. Maybe there's something wrong with how we were optimizing. Yeah, I don't know, but this is taking way longer than the other one. Optimization type equals pal axis dot scatter data of valid region types. So now, what's the problem? For C param and enumerate best params dot keys. Best params of param is equal to best param data of param dot mean. So the problem comes, the optimization runs fine. The problem comes when we're plotting. Optimization runs fine. Problem comes when we plot. So, all right. So the reason that is because it's going for each one best params dot keys. So if param is equal to Oh, nice. We could just fix it when we're doing the get best params. So if param not in percent return for profit, then add the param to best params, otherwise don't add it. Now let's try optimizing again. And we can optimize, go back to the circle optimization because, well, we fixed the problem with the circle optimization, but there's still not the region plotting. So free circle. And we're going to say the optimization type is Bayesian. All right, now the Powell optimization is finished. And what did it find? Nice. Okay. So what if we do the Powell method, but we say, let's get a free circle. Okay. Now back to implementing optimization types. Hi, Zihins. I don't have a name for it yet. I have yet to name it. You could find the GitHub. Go check out the GitHub. It's in the description right here. I'll send that in a link. All the data is in there. I still have to update it with the code that I'm writing now, but there's the link to the GitHub. Thanks for watching. All right, so we're going back to try to implement the other optimization types. Now, simulated annealing. We have a large search space, so that would be good for us. And lots of local optima too. So this is something we're going to want. Hi Zihins. I don't have a name for it. Don't currently have a name for it. The application is this code, and I'm using this code to run analyses that I'm putting in here. Eventually, I'd like to have something where anyone could go do these sorts of analyses on their own data, so people can go identify their own betting trends. So let's see if we can get simulated annealing in Python. Nice. Oh, basin hopping. Okay. So it says use SciPy basin hopping instead of simulated annealing. All right, so this will be easy to implement. So we need an initial guess, a function, and that's it. Do we even need bounds? No. Okay, cool. So we just need a function and an initial guess. The temperature parameter for the acceptance or rejection criterion, higher temperatures mean that larger jumps in function value will be accepted. For best results, T should be comparable to the separation in function value between local minima. Okay, so T defaults to 1. We're probably going to want to make our T smaller because we're using percent return. So the differences in between our local minima will probably be pretty small. Okay, so back up here, let's add a new optimization type. And simulated annealing. Okay. From scipy.optimize import also basin hopping. Okay, then down here, elif optimization type is equal to simulated annealing. We can say copy this. Then we're gonna say res is equal to basin hopping of optimizable func x naught, and then t is equal to 0.1. Okay. Now back to looking at the Powell method for free circle. Nice. Now let's go look at the plot we got. Okay, nice. So the Powell method for free circle gives us something. We're not doing the test, but that looks like a really good region. That looks like the type of region we would want to keep betting on. So now, can you help me please? I have big problem is that of SPSS statistics, I have a big problem with my license key. So there is a way to divert. Zihins, I really don't know what you're talking about. SPSS statistics is like a statistics package, I think. And if you have a problem with your license key, I don't know what to do about that. Probably the people at SPSS would be best to contact. Okay, so Powell method worked. Now let's try, we don't want to look at test num-years to go back yet, but we do want to perform optimizations on this. if perform optimization analysis is equal to true. Okay, so the region type we're going to do is free circle. And then optimization type is we're going to use the Powell method. Now let's make sure that's on, perform optimization analysis. Okay, that should be good. All right, let's run it. Hey, no inconvenience, Zihins. I hope you get it figured out. I wish I could be more help. I don't know what I could do. Good luck though. I hope I hope you can find luck in your statistics journey. So you're using SPSS right now. Do you ever write code for anything? Comment in the chat. Oh, Zahindula. Oh, okay. Am I saying that right? Zahindula. Sorry about that. Zahindula. Good to meet you. Thanks for watching. Yeah, comment in the chat if you use any coding languages regularly. Oh, basin hopping. Can't import basin hopping. Good to meet you, Zahindula. um, so basin hopping isn't importing. From SciPy to optimize import basin hopping. Oh, basin hopping, one word. Perform optimizations. Simulated annealing. Basin hopping. Okay. And then if it's simulated annealing, do basin hopping. Okay. Now let's run that script again to do the analysis for the free circle. Okay, and it's running. Everything here is running now. What was going here? These two have, no, that one continues to run. So let's go look up group optimizations. Um, hmm. These look like they're all currently going. 12, 16. Oh no. None of these are currently going. What? Oh, that's right. I just forget. My time's messed up. Huh. So it says on 2016, $0 return in profit. So I guess we rewrote the percent return to be -1 if we're, or profits -1. Man, that's not what we were hoping. We were hoping for that. Man. Okay. So 2023, 12, 16. Let's look at the results. Oh, it just gets nothing for every year. Yep. Well, so much for that. So it found this pattern down here. What? Is something different happening when we're doing a group optimization? Because I just don't understand why this would work. That's what I've been trying to do this whole time. Okay. Well, anyway, let's go focus on getting the other stuff implemented. So back to the optimization types of black box optimizations. So let's go test simulated annealing. Tests, perform optimization analysis. Let's take that off. Now we want to do test optimization and optimization type should be simulated annealing. Okay, now let's go run that. Simulated annealing is not, oh, hi. Simulated annealing isn't in there. So what do we call it in here? Simulated annealing. It is in there. Simulated, oh, annealing. So test optimization, simulated annealing. Save it and run it. Okay, so that works. Yeah, Zihingela, sure. You could follow along on here and just put comments in the chat um, as you go. Um, I can, so I'll do a like more instructional live stream soon. That will be easier to learn on. Because several people have commented wanting to learn. But this is kind of an awkward format because if you're building something yourself, you really need to, get feedback. Hey, I'm struggling with this thing. Help me. One way you could get involved is collaborating. So I'll put all this code on GitHub soon. If you don't have a GitHub, you should make an account if you're interested in coding. Then what you can do is go to the repository here. It's in the description for this live stream, but I already sent it in the chat. But you could go to the repository, make a pull request. That just means getting it on your local computer. And then you could make a change to this and upload your change. So we could do that with a simpler repository. I'll just send the link again. Do that with something like very basic messing around with data or something, and that could get you used to working with code. Um, and that would also be good for the other viewers who want to do similar sorts of things. Um, so, okay, our simulated annealing optimization finished. So let's go check on that. It's not a group optimization, it's a single optimization. Wow, that did terrible. Um, huh, that's interesting. I wonder what it looked like as it looked through the parameter space. Um, let's open this in Excel, then we could go look at it. The parameters seem to not change very much. Or I guess profit didn't change as the parameters changed. So let's go see how did the parameters wander around over time. Okay. Now this might be a problem with our t value. The t might not be big enough. Yeah, k barely moved at all. H didn't move at all. R barely moved at all. So what if we try with a smaller t? T equals 0.1, so let's try t equals 0.01. And then let's run the simulated annealing again. Now let's exit out of here. Don't care about those changes. All right. Now back here, what else do we want to add? Added easy implementation from SciPy. And then the last thing is need to tweak params, possibly t, because it does not look through a wide range of search space. Okay, now stochastic optimization. See if we could find that. Oh, okay, so simulated annealing is stochastic. Oh, so yeah, stochastic just means there's randomness injected. So, let's pull this notepad file back up. So stochastic, broad family of optimizations with randomness includes simulated annealing and differential evolution. So no reason or way to implement. Way to implement. What's an econometric character? Zahingila? What is an econometric character? Well, actually, yeah, what are you saying is an econometric character, and also what is an econometric character, period? Um, all right, so we're almost done implementing different optimization types. Oh, this one finished. So let's go check on that and see how it did. Got the same exact result. So let's go look at that and see what, if we lowered the t, did the parameters look around anymore, is the question. So this is with the t lowered. Now how does the h parameter move? Oh, it still barely moves. K barely moves. And R barely moves. Okay. So let's go make a note. Oh, wrong PowerPoint. So our note, we're gonna say, gonna call this simulated annealing. Does not look through a large enough parameter space. And just to prove that, we could say, look at these plots. Okay. Now let's screenshot, and we'll throw that in our PowerPoint. Pictured is results from simulated annealing with T temperature equals 0.1, moving, decreasing T from 0.1 to, what do we decrease it to? T to 0.01. From 0.1 to 0.01 did not have an effect. Okay. Now let's make that smaller. Paste in our plots. From simulated annealing on free circle with t equals 0.01. Okay, and then let's put in that plot. Okay. Now back to here. Exit out of the Excel. Oops. We want that. We just don't want this. Oh, econometrics. These are plots of odds. I'm not dealing with anything with the economy unless you're just talking about this being a free market. When I'll just show you really quick what this is looking at. So if we go to, so this is all sports betting stuff. So OddsShark is a good site for sports betting. So if you go to any bets, what I'm looking at here is football stuff. So if you go to any game that's taking place, they open the betting on the game like a week or two before the game begins. And then the odds of the game change as time goes on. So here the home team was minus 135. That means you had to bet $135 on the home team to win 100. And by the time the game closed, it was minus 125. So that isn't a big significant difference. But some teams have a large difference. And if you know how the odds are going to move, you can capitalize on that. So in this plot, We're looking at on the x-axis is how much the odds have changed for the away team, and the y-axis is how much the odds have changed for the home team. Oh, so you're saying it's an econometric character. Are you saying it looks like an econometric graph? It looks like we're dealing with economy stuff, because if that's what you're saying, then I agree. So we want to, all right, subgradient method. We're almost done implementing our optimization types. So subgradient method Python. Okay, so this we could just say looks complicated and there's no easy implementation. Okay, then model-based algorithms, also complicated. Okay, so now we've finished adding optimization algorithms here. We started with differential evolution. Now we added Bayesian, Neldermead, Powell, and simulated annealing. So if our problem is that differential evolution's a limited optimization method, then we should be able to solve that problem here. So let's go to the Trello board. Now what do we want to do? We've added different optimization techniques. So that's done. Take bounds definition out of optimized line location. Could do that later. Generalize get results to return any value specified. Run analyses on all region types. Okay, so let's see how those are going. Training years test. Triangle and modified triangle. Modified triangle might be done. No. All right, so training on the modified triangle, training on 1 year of data. How did it do? Not great, but not the worst. I lost 86 cents in 2013. Yeah, so that's performing about the same as the other methods. You can delete that because we don't need it. Okay, now the rectangle method, also not getting very far. How did this do? Stupid Excel. We should open with VS Code. Okay, so this did actually terribly. But we kind of knew the rectangle method wasn't very good. Okay, so that will wrap it up for this stream. Now the next thing we're gonna want to do is there's some code stuff we need to do. I'm gonna do these optimizations before the next live stream. So then the only thing left will be we need to generalize get results. So basically code stuff will be left for the next live stream. So thanks for watching. I hope you enjoyed. Especially thanks for watching Zahingela. Oh, already create. Zahingela, are you talking about GitHub? Are you talking about GitHub? All right. Just seeing, not sure if you saw this, Zahingala. Um, Hopefully you could get squared away. If you don't, put a comment in here in the next 30 seconds, then I'm going to end the stream. Yeah. Otherwise, good luck. Hoping to work on some code with you. All right. Well, tune in next time if you're interested. Thanks for watching.